Hello everybody and welcome to the very first video for PK. I plan on making these throughout the semester. I'm not really going to cover any of the multiple choice content since it was kind of just stuff we learned in drug delivery and previously. Most of it was honestly the first video from Drug Delivery 1, so I'd maybe go back and watch that if you wanted help with that. But in this video I hope to cover a lot of the math. I know some of it's been a little bit trickier and some of the problems have been a little more abstract. So I kind of just wanted to go over some tips and tricks I use, how I kind of look at these problems, and how if he does throw us for a loop on the exam with some kind of weird problem, how you can kind of work through it. So yeah, let's get into it. Okay, so this was a problem he gave in class. It's one he solved with a graph. I kind of just wanted to show off. You can kind of do this one without a graph actually, in case he asks us something like this. It's a little convoluted, but you can get there. So what do we need in the long run to do that? So it's actually really helpful that we have this IV bolus dose. When we use an IV bolus dose, we can expect to use an equation like this, um, just for kind of basic decay, which is really nice. We see that it's 15 mg per kg. So if we do 15 times 35, right, 35 kilogram patient, 15 mg per kg, you get 525 to 2 milligrams is our total dose. That's not really the most prevalent thing right now. I just like going in order for the problem, but I'm kind of going to be bouncing around here. Um, Eventually, we will need to find out this IV infusion kind of steady state, which is this equation right here. So I guess that would have been a good thing to go over first. But essentially we have R0, right? That's our just basic rate. That's this 3. We need two things from this. We need our K10 and we need our VD still. These are unknown. So that's what I'm essentially solving for and what we can shortcut. So the K10 is actually easy, kind of. We don't have an exact half-life, right? But we can get it from this chart because we know the IV infusion is stopped at some point. And we know this is decay over these 2 hours. But how do we kind of set this problem up? Well, if you recall that half-life, or at least the hours of half-life, is equivalent. So this is 2. This isn't quite a half-life because, right, from 3 to 2, it's like a 66% life. But we can still use it in the equation, is equivalent to our K10 value in the denominator divided by, and in this case, it's actually the natural log of 2 over 3, aka it's a 66% life. And I think this is technically a negative K10 just to make signs add up. But the point is we can actually isolate this, right? So we can move K10 to this side, can divide 2 on this side, so the natural log of 2/3 is negative 0.405, which means that k is equal to 0.405. All of a sudden, we have another part of our equation. This is really good for us. Now what we can do, I'm going to erase some of this just because it's getting in my face. How can we get that kind of volume of distribution? A few ways we can do that realistically. I think the way I would like to do it the most is we're going to use this equation. We're going to find out what the plasma concentration is at time 0, right? So time plasma concentration and time 0. So this isn't the hardest thing to do. It's just our one issue with it is we kind of need to figure out um, we need to reverse engineer this equation too, essentially like we did with this, right? So what we can do is we can actually solve one side. So we know that, let's say at time 0.5 hours, we have a concentration of 9.4. It's equal to concentration of the plasma times 0. We don't know what that is. But what we do know is we know that E to the negative 0.405, right, that's our K value, times 0.5 hours is equal to this. This is the plasma concentration at this time. So we can divide 9.4 by this E term over here. And once we do that, we can get that concentration times 0 is equal to by E negative 0.405 times 0.5. We can get that it's 11.5, and I don't know what this is. Oh, it's milligrams per liter. Perfect. Okay. 11.5 milligrams per liter. Then what we can do with that is we know that there's 525 milligrams kind of just per dose, right? That was that 15 times 35 we did up here, divided by 11.5 milligrams per liter. Milligrams cancels, units come to the numerator. All of a sudden we have a volume of distribution. So we have 525 divided by that, what we just calculated above. We get that the volume of distribution of this drug is about 45.6 liters. All of a sudden we have volume of distribution. So now we can get the steady state, right? Because it doesn't really matter that this is a 3 milligram per kilogram per hour infusion. Well, it does, right? It's our R0. But we can now find out when that gets there. And it's really easy because now we can just do 3 milligrams per kilogram. K10 is 0.405. And then our volume of distribution is 45.6. It's multiplication. And when we put that in our calculator, we get that the steady state concentration is, I might have put this in my calculator wrong, or maybe I didn't. I think I might have. Oh, because this is milligram per kilogram per hour. Right. So we need to multiply this 3 by 35 as well. So 3 times 35 is 105. Okay, I'm like, why is my plasma concentration smaller than... Okay, so make sure to do that, right? When you're given these infusion rates that are weight-based, we need to multiply everything, which I did above for the bolus dose. I did not do for the infusion dose. So don't make the same mistake I just did. Anyways, when we divide 105 by 0.405 times 45.6, we still get a number that doesn't make sense. We got 5.68. Now, why is that? Yeah, that's just definitely not the steady state concentration. Hang on, I'm gonna go back and I'm gonna find where I made my mistake in my work. Okay, I'm back, and also I can't read problems. So let me kind of explain what just went on there. So kind of what we've been doing up into class into this point, is we've been kind of matching bolus doses with their rate of infusion, right? Which is what you want to do in practice therapeutically. This dose of 15 mg per kg, I was right when I calculated the steady state that this infusion would have. So essentially what the graph of like plasma concentration would look like is we have our bolus. Let's start with it. It'd be like this. It'd go up really quickly. And then actually when we start doing this infusion, ideally what we want, right, is after it peaks, we want a graph that looks like this. We want it to be steady. When we do this infusion at this rate, this 3 milligram per kilogram per hour plus our bolus, what we get is we get something that looks more like this. It kind of evens off. It actually initially peaks because this bolus is too high. Now maybe this is the steady state we want right here, right? This kind of area. We wouldn't want it up here, so we start with like a higher dose and then we kind of just taper it off a little bit lower. An example of this, I suppose, could be, let's say you have kind of a bacterial, you're doing like broad spectrum antibiotics, a mix of them, and you want to start with some peak dependent killing. You kind of have this first peak, right? But then you kind of move into more a concentration dependent killing regimen, right? You lower that dose a little bit, but you keep it at a steady state just with those mix of antibiotics. This could be an example of when you do that. But this is an example when the bolus dose actually doesn't match up with the steady state. And that also wasn't even what this problem was asking. I'm just dumb. It was literally just asking how long is it going to take to reach the steady state. So the second we got that K value, which was that 0.045, or yeah, I said that right, 0.045. It's just asking how long is how many half-lives. So if you remember, our half-life equation is 0.693, that 0.045 in the denominator. So if we do that really quick, 693 divided by 0.405, we get 1.7 hours. Now we just multiply that by 4.5, right? Because 4.5 half-lives is when that reaches that steady state. And boom, we get 7.7 hours. That was needlessly complicated. I'm not going to re-record that. Now you know how to calculate steady state from that as well. I still think it's useful, but yeah, oops, bonus problem, I guess. But that's how you get that. Okay, now let's do this problem. So this is another one that Dr. Desai gives in class. It's a lot of steps. I think it's decent. It shows off something really good about the infusion rate problems. So this patient, I don't care what drug this is, they have a body surface area of 2.2 meters squared. Drug is dosed at 175 milligram per meter squared. Let's do that really quick. 175 times 2.2. All of a sudden we get I divided in my calculator. That did not look right. It's been a long day. Okay, 385. Perfect. For reference, I was recording the fundamentals video right before this, so 385 milligrams. But this is kind of like a bolus dose, right? This isn't what we're gonna infuse. We're gonna infuse this over the period of 3 hours. So this 385 milligram is great, but it's not our R0, which is what we need right here. So what we need to do is divide that 385 by 3, and now we get 128.3 milligrams per hour. So we're making progress, right? And we're using this equation because it's just showing plasma concentration after a certain time of an infusion. Pretty basic equation. Next up, we actually just are given our volume of distribution. Very handy. So we got that part of the problem. Only variable left, really, because we know our time, right? Our time is going to be that 3 hours, at least for the first one. Only thing left is our K10, but we do have our half-life. So it's just a matter of setting up our equation. Hours in half-life equals 0.693 over that K10. Move this to this side, divide this side by 12. 0.693 divided by 12 is 0.058. Perfect. Now we can just do this equation. So it's just plugging numbers now. So for R0, we have 128.3 divided by 212 times 0.058 times 1 minus e to the negative 0.058 times our 3 hours. The reason we're doing 3 hours here is because whenever an infusion is like just stopped, that's peak concentration, unless it's like steady state. I mean, it still is peak concentration at that time. It's just with the steady state assumption, it might have happened earlier. But what we can do now is just simply plug in numbers. 128.3 divided by 212 times 0.058. Multiply that by 1 minus e to the negative 0.058 times 3. We get a concentration of 1.67. I'm assuming this is probably milligrams per liter. If it wasn't, it is now. So that's great. So this is our concentration at 3 hours. How do we get our concentration at the end of this 24-hour period? So now we need to use a different equation, right? We're no longer infusing, so it's simply a decay equation at this point. We have our concentration at T, which in this case is CP3, right? Is e to the negative K10, we know K10, and we have our time essentially after the infusion. So if it's a 24-hour period and we've done 3 hours of it, we have 21 hours left that we're going to decay this for eventually, and that'll get us our concentration at this new time. So we're going to do 1.67 e to the negative 0.058. Then T is 21 hours. That'll just be our final equation. I'm going to box this in too, just so we remember that was one of our answers. Times e negative 0.58 times 21. We get our concentration to be 49. Yeah, just 0.049. I could do more digits, but why bother per liter? So does this answer make sense? So basically, right, one half-life is, 12 hours. Two half-lives then would be 24 hours. This is 21 hours, a little bit less than that. But if you remember a rule about half-lives, each one takes a half off, so one half times one half is like a quarter, it's 25%, right? Since this wasn't quite two half-lives, this should be, around 25 to 30% of this dose-ish kind of range. Does that make sense from this 1.67 to this 0.5, 0.49, 0.5, same thing? Yeah, so I'm okay with this answer. This seems right to me. Um, and that's how you go about solving one like this. Okay, so for these next couple problems, these aren't problems we got in class. They take similar concepts from the homework problems. They're different problems. I kind of just wanted to show how to work them because they are harder. And I added some caveats that I just think are kind of important reasoning-wise for the exams. I also, when I was kind of designing these problems, I cut out a lot of the multiplying by body mass, just the tedious work, so I could focus on kind of the concepts behind some of these more difficult problems. So what do we have first? We have a patient receiving 96 milligrams per day of a prodrug. This is an essential thing I added in this problem. And it'll make a little more sense in this second part right here. And it's essentially wanting to know what's the steady state of this prodrug. For the first part of this problem, this isn't super hard. One thing we do need to do is, I like this in this problem, incorporating this equation, is we're given volume of distribution and a clearance, not K10. This is also on our equation sheet, which is really nice. But if you remember, clearance over VD is equal to K10. So if we have 50 over 40, our K10 is 1.25. And you might be thinking, Ryan, that's really high. Yeah, I didn't really check these numbers before I went into this. So anyways, we have that. Um, so next up, and for reference, it's steady state equation, right? So really basic. We have K10, we have VD. The only thing we need is R0. We almost have it. 96 milligrams per day. Remember, whenever we have an R0, we need to convert it to kind of like an infusion rate, because we're asking for the steady state of a continuous IV infusion. So, what is our R0? It's 96 milligrams per day, but kind of the caveat right here is that this clearance was in hours, right? Our K10 is in hours to the -1, technically. We never really write units on K10, but it is there. So it's important we convert this infusion rate to an hours or K10 to a day. I'd rather convert this to hours. Why? Because I set this up to divide really nicely. 96 divided by 24 is 4 milligrams per hour. So now we simply do K10 is 1.25 times volume of distribution is 40. We get a steady state of 4 divided by 1.25 times 40. We get 0.08 milligrams per liter times hour. So I'm fine with that. So what do we, or this isn't liter per hour. I think this cancels. The steady state is 0.08 milligrams. That's all that matters. Forget all that other stuff I wrote down. But anyways, so this is our answer to point 1. As you can see, that steady state's pretty low. I mean, maybe this is something like a chemotherapy drug, right? Something that's not really going to need a high concentration, going to have a narrow therapeutic index. This is definitely per liter. What am I saying? Yeah, because hours cancel. You see, if I don't write down my units, but the hours cancel here and here, but this is also a liters. The point is it's 0.08. But now we have this problem, 200 nanograms per milliliter. We're going to convert this to, what are we going to convert this to? I haven't worked these problems ahead of time, just FYI. I know how to solve them. I just don't know if the numbers make sense. We'll just say we want it to be 1 milligram per milliliter is what we want the active to be. Do we accomplish that right now with our current IV infusion? No, not even close. We are like 1/12 of the way where we need to be. We need a bolus dose to get us up there. But there's another caveat. The reason there was a prodrug in the first problem is that only 60% of the prodrug, excuse me, is converted into the active form. So how much prodrug bolus would we need to get an active concentration of this? So this actually, I just drew an arrow here prematurely. If you remember, since this is just our prodrug infusion, this is our prodrug concentration. This is our active concentration that we want. And then another caveat is that our answer is going to need to be a little bit higher to account for that loss in metabolizing a prodrug to an active drug. So what's our loading dose we need to reach this level? This isn't super hard to do. We can essentially kind of shortcut this, right? We know we want our active concentration to be 1 milligram per milliliter of active drug, but we know that our prodrug concentration will be higher, right? If only 60% gets converted, that means we have 40% loss in that conversion. So how do we do this? Whenever you're given a percent like this, and you are trying to look for an active drug concentration, but you're trying to, how do I word this correctly? When you are giving a drug as a prodrug, but you are observing an active concentration of the active drug, you will want to divide by the metabolism percent. If you are given the concentration of a prodrug and you are dosing the prodrug, then you multiply by the percent. Because if you multiply by the percent, it'll be lower, your final answer. This will represent kind of the loss. However, if you start with the active concentration, I'm saying this, but let me just draw a chart. This should be easy. So, right, let's just say it's a problem. You're administering a prodrug. This is always the same. And you're given plasma concentrations. You're given the concentration prodrug in the plasma and the concentration active drug. If you're given concentration prodrug, you're most likely looking for concentration active drug, right? And vice versa. If you're given concentration active drug, you're looking for concentration prodrug. How do you do this? If you're given concentration prodrug, which in this case we are not, we have to multiply by loss percent, right? So let's say this is like 50%. If we multiply by 50%, it's going to be smaller. And this makes sense, right? Because we lose some of our prodrug to the active drug concentration is going to be lower. Now, if we're given the concentration of active drug, this is what we are given. This is this 1.1 milligram per milliliter. We divide by our percent. So we divide by 50%. This means we need our prodrug concentration to go up in order to account for those losses, right? Because we know that if we have 50% of our drug loss, but we do want a certain active concentration, we need our number of prodrug to be bigger, which is what we need right here. And I chose 50% arbitrarily here. 60% is what this problem says. I hope that kind of makes sense. If not, pause this part, rewatch it. But just, it really depends on if the plasma concentration is the active drug or the prodrug. I cannot stress that enough. Yeah, but anyways, with that out of the way, we can finally solve this problem. So we're looking for the concentration of our prodrug in the plasma now, right? Which is really simple. It's just 1 divided by 60%. That is... We need our concentration of prodrug in the blood to be 1.67 milligrams per liter. Now what we can do is, I'm going to erase this. We don't know per se what we need our initial prodrug dose to be, right? Prodrug dose. But what we do know is the volume of distribution, right? This is like a raw total dose over a volume, and we do know that. We know our volume distribution is 40 liters. So it's really simple. We just multiply 40 over to this side. 1.67 times 40 is 66.7 milligrams. And that's our initial prodrug dose, which is pretty high. It's a lot higher in this problem, right? Because if you remember, our concentration or infusion is only 4 milligrams per hour. We're going all the way up to 66.7 milligrams. That is 15 times higher. It's like 16 times higher, actually. So, and this kind of makes sense, right? Because this dose right here, or this concentration in the plasma was so low, these milligrams per liter, we need a really big prodrug initial dose to kind of get us up there. So that's how whenever you see a percent, just remember that chart. Am I multiplying or am I dividing? And it just depends. Do you have the active in the blood or do you have the prodrug in the blood? And that's kind of how you can distinguish it. Okay, so here's another custom problem. Again, this is kind of similar to one of the homework problems, but I did change it up in some key ways that I just kind of want to highlight. For this first one, it's just asking for an IV and a maintenance bolus loading dose. Let's start off with bolus. It's a little bit easier. This is very similar to how we kind of solved the last part of the last problem, kind of that last step. We have our desired concentration with the bolus dose being 10 milligrams per liter. We don't know what our dose is. And luckily in this problem, this is an active drug. There's no worry about a prodrug. There's no worry about really metabolism. So what we can literally just do is our volume of distribution is 50 liters. Our bolus dose, or BD, just that over 50. So it's as simple as 10 times 50. It's just 500 milligrams. So that's an easy one. Our infusion rate, kind of maintenance dose, we do want it at this 10 milligrams per milliliter. This will be this equation down here. So the steady state is 10 g per liter, not milliliter, sorry. R0 we don't know. That would be our infusion rate when we get there. K10 we do know. It's 0.1, pretty simple. Right. VD is 50. So we just have 10 times 0.1 times 50. And we get that our R0 is equal to 50 milligrams. So we'll just call it infusion, 50 milligrams per hour is what that is. And that'll get us to steady state. So again, that's like a really simple problem. I made the numbers easy because I didn't want to calculate hard things, but just kind of showing where you put those in the equation. That's how you can do this relatively easily. Yeah, so now kind of where the caveat to this problem comes in. This drug has hepatic clearance. And in this world, drugs are only cleared two ways, right? There's no, degradation by bacteria or anything like that, or sweating it out. Drugs are either destroyed by the liver or destroyed by the kidneys with this drug. And how much are they destroyed by each? Well, you can see here that 50% is cleared via the kidneys and 50% is cleared via the liver. It's a perfect balance. This is like the perfect drug, right? So we know that our total clearance equals 100%. At one point or another, 100% of this drug is going to be destroyed by either the liver and kidneys, and it's going to be half and half. So our clearance, this 100%, is essentially equal to, in a normal healthy person, 50% renal plus 50% hepatic. Makes sense, right? This is a perfectly balanced drug from these ratios, these 0.5s up here. But this guy, he has liver failure. He has hepatitis or something. This 100% isn't going to be him. He's not going to clear this drug as much as a 100%, aka a healthy person, right? Eventually, 100% of this drug will be removed from the body. That's not what this 100 represents. This 100 represents kind of a baseline normal person. So what's our number in an unhealthy person? Well, assuming that hepatic clearance is reduced by 50% when somebody is sick, we have 50% renal clearance still, plus 50% hepatic clearance normally, but then we actually have 50% of that 50%, right? Because half the liver is destroyed at this point. So what we really have is we have 50%, and that's our renal. And then plus, what's 50% times 50%? It's 25% hepatic. So we get this person's baseline liver function or elimination function is 75% of what a normal person is. Now, if a person is eliminating drug less, right? They are worse at getting drug out of their bodies. Do we want to give them more or less drug, especially if it's narrow therapeutic index? We want to give them less because we don't want to overload them on drug. Since they can't eliminate it as fast, we're going to lower their dose. And this is really easy. All we have to do is we have the 75%. And luckily, this is like a scalar value. The math isn't very hard. You are literally just multiplying these two numbers by 75%. So for our bolus, it's 375 milligrams, right? Because it's what 500 times 75% is. For our intravenous, 50 times 75%, 37.5 milligrams per hour. And boom, that's how you do that problem. So again, the key isn't whether or not these numbers add to 100. The 100 is just a baseline characteristic. What the problem is kind of how do we dose drugs in somebody that's not at baseline. But yeah, that's pretty much all of these. If you have any questions, feel free to email me, message me before the exam. I tried to get this one done a couple days before, just in case anything came up. Hopefully this helps a little bit with the homework problems. Obviously they're not one for one. I did change things up and add little caveats here and there just to differentiate them enough. But I know some of those homework problems were tough, so I'm hoping that at least kind of these baseline methodologies might help you to work them. But with that, thanks so much and see you next time.